Well, in section 3.1, we proved that all first-degree polynomials, in other words, lines of the form f of x equals mx plus b, are uniformly continuous. All lines, all degree 1 polynomials are uniformly continuous. We also showed that, for example, this polynomial is continuous at x not equal 2. We later found out that we discovered that all polynomials are continuous on the entire real line, their entire domain. Fact: no polynomial of degree greater than or equal to 2 is uniformly continuous on R. We did see that f of x equals x squared. We proved that that's not uniformly continuous, and no polynomial of degree 2 or greater is uniformly continuous, basically for the same reason. Maybe you remember from calculus or pre-calculus that if you have a polynomial of degree 5, it might look like this. Might look something like that. 5 ups and downs, maybe. Eventually, it either rises right or falls right. That's the terminology we use in pre-calculus. And left, eventually it either rises left or falls left. This one falls left and this one rises right. So the problem is, as x gets bigger and bigger and bigger, if we have a fixed value of delta, it's not going to be sufficient. Remember in the f of x equals x squared, for a fixed epsilon, our delta had to continue to shrink and shrink and shrink and shrink until it approached 0. So maybe this picture doesn't help, but let's go ahead and prove that this polynomial, the same one, is uniformly continuous from the interval 0 to 5. Okay, once again, I wrote down the definition. For every epsilon greater than 0, we have to find a delta such that when x and y are in the domain and very close to each other, less than delta apart, then their heights, or the values of the functions, the difference between them, f of x minus f of y, is less than epsilon. So as usual, we have to take an arbitrary epsilon, and then we are going to choose delta. And I don't know what value of delta is going to work, so as I frequently do, I'm going to leave it blank for now, and let's just see what happens. Maybe I can fill that in at the end. Thus, if this is true, if x minus y is less than delta, I'm assuming that x and y are in the domain, so we're dealing only with numbers from 0 to 5, strictly in between 0 and 5. That implies that f of x minus f of y in absolute values, which we know what that is. We can just plug it in. Here's f of x right here. 5x squared plus 2x minus 3 minus f of y, so we'll plug a y in and we'll get 5y squared plus 2y minus 3. And don't forget the parentheses there. Okay, I think I have several more lines, so I'm going to go out one more equals out here towards the right and simplify that a bit. What can we do in our heads here? I know I have a 5x squared minus 5y squared. So I'm going to say 5 times x squared minus y squared. The minus 3 and the minus 3 cancels out, and all I'm left with is a 2x minus 2y. So I will call that plus 2 times x minus y. So that was just simple algebra. And I think I'll continue on right about here. This is the difference of two perfect squares, x squared minus y squared. So I'm going to call that 5 times x minus y, x plus y. I just factored the difference of two perfect squares. plus 2x minus y. And I think I'm going to go one more to the right, and then I'll be able to proceed down. Well, notice that each of these two terms has a common factor, which I'm going to pull out. So I'm going to get in absolute values, I'm pulling out the x minus y, and it's going to be I'm going to be left with 5 times x plus y plus 2. 5 times x plus y plus 2. Well, by the properties of absolute values, that's equal to the absolute value of x minus y times the absolute value of 5x plus y plus 2. Just by the properties of absolute value. So I basically took that absolute value and that absolute value and we multiply them together. Well, we're really close. That is strictly less than what? Well, we found our x minus y that we needed to have. X minus y is less than delta. So I know that's less than delta times this. Now, can we figure out, I need something bigger than this. I need an upper bound for that number, that positive number. And the upper bound I'm going to use is, well, here's a plus 2, and we're multiplying this by 5. I need to make x plus y as big as possible. How big is big as possible? Well, x and y are both taken from this. So the biggest x plus y could possibly be is 10. And actually, it couldn't quite be 10. Because the numbers x and y are strictly between 0 and 5. So let's see. That would be 10 times 50 times 52. Maybe I'll go ahead and say the reason for that is because x and y are are strictly less than 5. Because of the domain we set up for this function. So 52 delta. I want that to be my epsilon. I'm going to force that to be my epsilon. Okay, so 52 delta equals epsilon is equivalent to saying that delta is epsilon over 52. I'm finishing the proof right there, but I do need to remember to put delta equals epsilon over 52 to make it all work out. And that is the end of the proof.